guys, this is Layla. Today we'll speak about fatty acids and glycerol. Alright, so the synthesis of fatty acids occurs primarily in the liver and the lactating mammary glands, and to a lesser extent in the adipose tissue. Now this is a cytosolic process that incorporates carbons from acetyl coenzyme A into the growing fatty acid chain using what? ATP and NADPH. Here's what's going to happen. So from triacyl glycerol, you're going to get glycerol and fatty acid. The fatty acid will become fatty acyl coenzyme A, which can produce acetyl coenzyme A, which goes into the citric acid cycle. And you know that we get triacyl glycerol from the glycerol 3-phosphate coming from glycolysis. Now, I told you that it is a cytosolic process. So pyruvate is obtained from glycolysis in the mitochondrial matrix. So it needs to be transported into the cytosol. Now, this acetyl coenzyme A on its own cannot be transported. It has to become citrate with the enzyme citrate synthase combined with oxaloacetate, the first step of the Krebs cycle. And this citrate can cross the inner mitochondrial membrane and go into the cytosol. In the cytosol, with the help of ATP citrate lyase, which breaks it down, it can give us the initial products, which are acetyl coenzyme A and oxaloacetate in the cytosol. Okay, let's start with the reaction. First of all, the acetyl coenzyme A should be carboxylated to form malonyl coenzyme A. This is catalyzed by acetyl coenzyme A carboxylase, and it requires carbon dioxide and ATP. The coenzyme of this is vitamin biotin, which covalently binds to the carboxylase enzyme. This is both the rate-limiting and the regulated step in the fatty acid synthesis. So the main step, there is allosteric activation by citrate, and because it is CAMP-mediated, the synthesis is activated by insulin. It is inactivated by the product itself, the long-chain fatty acid. So it is inactivated by epinephrine and glucagon, which are the counter hormones of insulin. There is also a long-term regulation. It is when a diet containing excess calories, low fat, causes an increase in the acetyl coenzyme A carboxylase synthesis, hence increasing the fatty acid synthesis, and in contrast, a low-calorie diet or a high-fat diet causes a reduction. For example, metformin is a drug in type 2 diabetes. It lowers the serum TAG by inhibiting the ACC activity. The remaining series of reactions is catalyzed by the multifunctional dimeric enzyme FAS, which is fatty acid synthetase. Palmitate, a 16-carbon chain, fully saturated long-chain length fatty acid, is the primary end product of fatty acid synthase activity. However, it can further be elongated. Now, FAS is multifunctional. From one acetyl coenzyme A, you're going to reach palmitate, which is C16, and acetyl is C2. So these are the different types of enzymes involved. You have acetyl CoA transacetylase, you have beta-ketoacyl ACP synthase, you have beta-hydroxyacyl ACP dehydrase, you have palmitoyl-thioesterase. These are different enzymes that are involved in the formation of the final palmitate. Desaturases present in the smooth endoplasmic reticulum are responsible for desaturating the fatty acids. Alright, let's review what we learned today. So from the glycolytic pathway, we have pyruvate going into the mitochondrial matrix. From here, we are going to get, remember, the pyruvate decarboxylase complex. From here, you're going to get the acetyl coenzyme A. With the help of citrate, it is going to come out into the cytosol. It's going to cleave into acetyl coenzyme A. Acetyl coenzyme A, with the help of acetyl coenzyme A carboxylase and fatty acid synthase, is going to give us palmitate, and that is our fatty acid synthesis. So the free unesterified fatty acids, they will move through the cell membranes of the adipocyte and they will bind to plasma albumin. They're transported to the tissues, where they can get activated to their coenzyme A derivatives and are oxidized for energy. Regardless of their levels, the plasma of free fatty acids cannot be used for fuel by erythrocytes, which have no mitochondria. The brain also does not use fatty acids for energy. Okay, moving on to glycerol. So glycerol phosphate is the initial acceptor of fatty acids during TAG synthesis. There are two pathways for the glycerol phosphate production in both the liver, which is the primary site of TAG synthesis, and the adipose tissue. Now, glycerol phosphate can be produced from glucose using first the reactions of the glycolytic pathway to produce dihydroxyacetone phosphate, DHAP. Next, this DHAP is reduced by glycerol phosphate dehydrogenase to glycerol phosphate. A second pathway, found in the liver but not in the adipose tissue, uses glycerol kinase to convert the free glycerol to glycerol phosphate. The glycerol released during TAG degradation cannot be metabolized by adipocytes because they lack glycerol kinase, as I said. Rather, it is transported through the blood to the liver where it can be phosphorylated. The resulting glycerol phosphate can be used to form TAG in the liver or can be converted to DHAP, where DHAP can participate in glycolysis or gluconeogenesis. Okay, before we finish, let's speak a little tiny bit about the regulation. Synthesis is lipogenesis, degradation would be lipolysis. So lipogenesis is greatest after a carbohydrate-rich meal and degradation in starvation. So high insulin and glucagon ratio will increase lipogenesis. Low insulin to glucagon ratio is going to increase lipolysis. So synthesis of lipids is primarily in the liver, degradation is in the muscle and the liver. The product of lipogenesis is palmitate and the product of the degradation is acetyl coenzyme A. And that is it for this video. I will see you in my next one. Bye!